We're going to conclude our treatment of complex equilibrium systems by talking about a very important equilibrium system that takes place in the environment, and that's the effect of carbonic acid. So our learning goals for this video will be to discuss the chemical role of carbonic acid, especially as it affects cavern formation, rain acidity, and especially ocean acidification. So let's first learn a little bit about the chemistry of carbon dioxide, and we'll go through this relatively quickly so we can talk about the fun stuff. So the solubility of carbon dioxide forms carbonic acid in water. It goes by this sort of chemical equation. So the carbon dioxide dissolves in water to form an aqueous solution of it, combines with the water to form carbonic acid. And this has an equilibrium constant of 1.3 times 10 to the minus 3. Now this can undergo acid dissociation, so it'll dissociate to form the bicarbonate ion, HCO3-, and a hydronium ion, with the equilibrium constant of 3.4 times 10 to the minus 7. There can be also another subsequent acid dissociation that would give rise to carbonate ion and hydronium ion, but this has a much lower equilibrium constant of 10 to the minus 11, so it's really the first two that are going to, at least initially, be our primary focus. So the net equation for all of this is when we have carbon dioxide dissolved in water, it combines with the water to form the bicarbonate ion and a hydronium ion, and that has an overall equilibrium constant, which is from the first two equilibrium constants of 4.5 times 10 to the minus 7. Now, why is this important? Why would we care about this? Well, the first two reactions basically establish that there is a slightly acidic solution. And the fact that this is slightly acidic means that carbon dioxide in the air, when it combines with water in the air, makes all rainwater slightly acidic. So this isn't acid rain. This is normal natural rain, is naturally slightly acidic, has a slightly acidic pH. But the third equilibrium is also important because it's controlling the amount of carbonate in the solution. So even though it hasn't been hooked into that net equation down there, the elements that appear in the net equation are going to be important because they will affect the position of the equilibrium for that third equilibrium and determine how much carbonate ion is present there. So let's see what effect this has. In our area, we have a lot of limestone caverns, and the reason that we have the caverns is because of this chemistry of carbonic acid. So what we want to know is what happens when slightly acidic carbonated water seeps into the ground. Well, in water, we're going to have the natural dissolving of calcium carbonate, which would form calcium ions and carbonate ions in aqueous solution, but it's a pretty small KSP, 3.36 times 10 to the minus 9. But it's enhanced when we have a little bit of acid in there. So now consider what happens when we have carbonate and some hydronium ion. It's going to form bicarbonate ion in solution and water. And this has a very big equilibrium constant, so you can assume that this reaction essentially goes quantitatively to the right-hand side. It also means, though, that calcium carbonate has its solubility enhanced by acid as well. So this is one of those cases where we have an ionic compound whose solubility is actually increased when there's a little bit of acid in the solution. And this is what that equation looks like. So let's go through this. We've got calcium carbonate solid and hydronium ion, so that's the acid in the solution. It's going to produce calcium ions in solution, bicarbonate in solution, and water. And this has a reasonably large equilibrium constant too, although it's not like the previous one, but 70 means that most of this reaction is going to go forward into products. So what that tells us is that when water that's got a little bit of acid in it hits limestone, it has the capability of helping that limestone to dissolve in the water. So because of that, we get limestone caverns. So it's essentially as the slightly acidic water is bubbling through the earth and going down into places where there's lots of limestone, it eventually eats away that limestone by dissolving it in this way. And by eating it away, it leaves these caverns deep underground. Now this also can help us understand why we get some of these crazy formations inside the limestone caverns. Now remember that when carbonic acid is in contact with air, maybe you didn't know this in the first place, but it actually has its equilibrium reversed. And so the carbon dioxide will degas And we see this all the time in carbonated beverages. A carbonated beverage like Coke or Pepsi is bottled or canned under very high pressure, and that very high pressure helps to keep the carbon dioxide in solution. But once we open it up to air and we relieve the pressure, that's when the carbon dioxide can come out. It degasses from that. Well, the same thing happens in caverns. You've got some carbon dioxide in the water that's going through these caverns, dissolving the limestone, but when it comes in contact with air, it can leave the solution and become gaseous carbon dioxide again. Now, what effect does this have on those carbonic acid equilibria that we saw before? Well, here is one of them. This was carbon dioxide reacting with water to form the bicarbonate ion and the hydronium ion. So now if I take some of that carbon dioxide out of solution and move it into the gas phase, it's no longer there for this equilibrium. So now we look at Le Chatelier's principle. If we remove one of the reactants, what happens? The reaction responds to replace that reactant. So in fact, what this does is it shifts the equilibrium back to the left. Okay, so that's great. It replaces the carbon dioxide. But what is it taking away when it does that? It's taking away some of the hydronium ion, so it's reducing the acidity of the water. Now this other equilibrium, the calcium carbonate equilibrium, depends on having that hydronium ion there, depending on having that acid. So if we're reducing the acid, what's happening in this equation? Well, we're reducing the acid, so that means not as much calcium carbonate can dissolve. So the effect is that it's going to shift to the left to replace that hydronium ion, and that means there's going to be less calcium present as an aqueous solution as calcium 2+ ions. So how does this work in a cave? Well, it's one thing to dissolve out the hollow that the cave is in, but now if the drops come through and they're open to air, they lose carbon dioxide, the equilibrium shifts to the left to replace the carbon dioxide, and it depletes the acid. The depleted acid now is replaced by shifting the second equilibrium to the left. What it's doing is it's causing the water that's dripping through the cavern to recreate stone, recreate limestone in the cavern. That recreation is what leads to these wonderful stalactites hanging from the ceiling of the cavern, and ultimately as it drips down and deposits calcium carbonate below, it creates stalagmites that grow up from the floor. So all of these wonderful cave formations that we're seeing are really due to this interplay of different equilibria that involve carbonic acid. Let's shift gears now and talk a little bit about the ocean. Carbon dioxide in the air gets absorbed into the ocean, and when it gets absorbed and becomes in solution, it forms carbonic acid there, and it's going to increase the acidity of the ocean, and in doing so it also decreases the carbonate. So as acidity increases due to increased carbon dioxide levels, the pH goes down. And the effect that this has is that we have fewer shells and other hard parts of marine organisms now coming into play. So here's what it looks like sort of on a microscopic level, and this is showing you all of those equilibria of various kinds involving carbonic acid. And I'm not going to go through detail in this picture, but it's useful to know that the same system of equilibria has this effect in the ocean, that it will in fact lead to less carbonate that is able to form shells. In the same way that it dissolves the limestone caverns, the greater amount of acid in the ocean dissolves away the calcium carbonate that forms these shells. Now, is this a thing we should be worried about? Well, in 1885, we had a pH of 8.2. If you move forward about 100 years, the year 2000, that pH had gone down to 8.1. You might say, well, big deal, 8.1 is almost the same as 8.2. Yeah, except that represents a 25% increase in the acidity. Now, what's projected is if we're on stay on the current trend by the year 2100, it will go down to 7.8, which means the acidity will have doubled. It's a 100% increase in acidity in the oceans. So there's a serious issue that's going to be happening at this point for all of those creatures that live in the ocean that depend on creating carbonate shells to protect themselves. And we can see that in this particular photo that shows pterapod shells now shown at various levels of acidity increasing as we go across and down. And we can see that it's not a very good effect. So as acidity increases, the carbonate-based shells dissolve in seawater. And here's an even more graphic demonstration of that. So some people have called ocean acidification the evil stepsister of global warming, and there's a lot of evidence mounting to show that this is a real concern of ours, and it's one that's all coming about because of the special chemistry and equilibria of carbonate.